Record
Yeah.
this. Okay, today Eric Wolf is going to tell us about
Okay.
his latest paper on TRAPPIST-1e once he gets his
Once I get
presentation up
my
here.
screen. Okay. I think there we go. Do you guys see the presentation screen?
No, we see your chat window from
Okay. You see
Slack.
my chat window. Okay. Okay. Let me find a different screen then. Sorry about that.
No worries.
Too many damn screens here. Okay. Ah, here it is. Stop share. Okay. Let's try this again. Okay. Stop two. Hold on. I clearly was not prepared here. If this doesn't work here, then
There it
still no
goes.
screen. Okay, there it goes. Okay, cool. We good?
Good. Take it away,
Uh,
Eric.
okay, so thanks everybody for showing up in these challenging times. And I'm going to give a brief rundown of the paper that I just published as part of the Champs ICAR team. I'm actually going to be kind of hustling through this hour-long seminar that I gave at UCR for Eddie's department last spring. So I will sort of hustle through that and skip over some slides to make it closer to 30 minutes instead of an hour. So the title of this talk, which actually doesn't quite match the title of the paper, is a large ensemble of chemistry and climate simulations for terrestrial exoplanets, a case study of TRAPPIST-1e. So, you guys already know who I am. I don't have to introduce myself. This paper, and here's the actual title: Chemistry, Climate, and Transmission Spectra of TRAPPIST-1e explored with a multimodal, sparse sampled ensemble. And I didn't update my slides. It's been accepted and published now in PSJ. It had multiple purposes. The first being the obvious scientific purpose of a study of TRAPPIST-1e coupling chemistry and climate and making predictions of observables, a very kind of standard thing we do in the field. The technical part of this was, which was a significant part, was developing a pipeline between the Atmos chemistry model into ExoChem with Karma for hazes into PSG, connecting all those three together, and then also doing this while leveraging a quasi Monte Carlo sparse grid across our parameter space, and then interpolating all the points together across the sparse grid where we use kriging, which is a version of Gaussian process emulation. And then programmatically for the Champs team, led by Kevin Stevenson and Ravi Kaparapu. This connects, two of our or three of our main task elements from the proposed work together. So it kind of is a demonstration of concept of yes, the team could work interdiscipline in an interdisciplinary fashion, connect all these pieces together, except for task one, they were our stragglers in the bunch here. But all right. So we chose TRAPPIST-1e because that's everybody's favorite planet. And we got this paper took so long to put together for a wide variety of reasons, which I won't delve into. Uh, but we were getting very nervous about the fact that, every step took so long, revision took so long, writing took so long. By the time this was getting published, planets B and D and or B, C, and D had all been ruled to have absolutely no atmosphere, or at most a very trace thin nothing of an atmosphere. Fortunately, right before this paper was published, there was a study published from Mr. Espinoza and I think a companion paper which I'll say do not unequivocally rule out high mean molecular weight atmospheres for TRAPPIST-1e. So as at the moment, our paper still remains relevant. There's still some hope that our N2 CO2 and methane parameter space studied in this paper may actually come to fruition. But even if it doesn't, part of the nature of this work was kind of bringing all the technical pieces together that we can apply to other systems, other parameter spaces, other planets in the future as part of the CHAMPS team as the ICAR project rolls onward. So, all right, next slide. All right. So our pipeline, simply put here, is we don't have reducing chemistry online in the model. That remains a challenging thing. I don't know, probably LMD's done it by now, but we don't. So we have Atmos photochemical simulations run offline, 1D beforehand. And then we feed those gas compositions and also haze production rates where relevant into exocam, which is fully coupled with Karma to simulate hazes. And then we have a self or a pseudo self-consistent model. Yes, one can argue that the temperature structure changes from in the 3D model can feed back onto the chemistry, but so it's I'll say it's pseudo self-consistent. It's pretty good. We're pretty happy with it. So in the simulation set, oh, before well, yeah, I'll say that in the simulation set we did 480 photochemical simulations, and then out of that, that's where we get this sparse sampling. We chose 32 points across that grid to do the 3D climate simulations because, as everybody knows, they're quite expensive. And Karma is sort of a beast of a code that slows the model down by a factor of 4 or 5. So that makes it even slower. And then once we take our self-consistent simulations, we run them in pretty standard approaches in the PSG, produce a variety of transmission spectra from that could be observed with JWST. And then this isn't in the paper. I'm not going to talk about this. As a follow-up, we've played around with some phase curves, but that's gonna get cut out of this talk. So, uh, so first we have this grid of 480 photochemical simulations from a fairly contrived set of atmospheric compositions, but we needed to start somewhere. So N2, CO2 up to 50%, methane up to 30,000 ppm for 1 bar atmospheric compositions. We realized this is sort of a contrived set, but we needed to start somewhere and not get too broad too fast and get it too unmanageable. And then from this set, you can see we found a hazy region where significant optically thick hazes would form. And we were actually you know, speculating that we maybe have more hazy cases to simulate. It only ended up a few of the cases out of the grid had hazes, but nonetheless, we simulate those. And then from that, tight grid of 480, we did a quasi Monte Carlo sampling across the grid of 32 points shown here. And then we simulate all of those with exocam and then exocam linked to Karma where relevant. I think there was 3 cases had very optically thick hazes. There was a couple cases that were in this fringe zone where they had a very thin haze that we did some sensitivity tests before spending the computational time for running another, 4 or 5 simulations with trace hazes that cost 4 to 5 times as much computationally. So we tested one of those to show that it actually did not have the hazes were thin enough and at this boundary region to not have a radiative impact on our cases. So we ran the 3 thick haze cases to completion, and this is just a smattering of all the different cases, temperature specific, community, cloud water. And then we chose in the paper, we choose 4 different kind of end member cases to do a deeper dive into high CO2, low, sort of the corner points, if you will, high CO2, low methane, low CO2, low methane, high CO2, high methane, and low CO2 and high methane. So kind of the quadrature points of all those simulations. And one of the things that you can see in the temperature plot here is these temperature inversions form in these cases. And yes, I will talk about that here shortly. So temperature profiles. If we take a look at we boil the mess of 32 down into the 4 corner points, you see them labeled here: low, low, high, and low CO2, high CH4 with hazes. And the X's here show where they are in our sampled grid. And what we found is that naturally there's a competition between the radiative effects of CO2 and methane. So as we know from modern climate, CO2 cools the upper atmosphere while it warms the surface. Methane is a greenhouse gas at low amounts, so less than about 1,000 ppm. And when it goes above that amount, especially under the red sun of TRAPPIST, it causes a strong anti-greenhouse effect from absorption in the upper atmosphere. So you can see here from these two curves. Whoops. Oh, crap. All right. Let me go back one. Sorry. From these two curves, we find the inversion here is not driven by the haze. It's actually driven by absorption from methane in the atmosphere, independent of the haze, because we see the inversion with haze and without haze, as long as there's high methane. And we can see that this when we look at some of the spectral characteristics at the top, we see the TRAPPIST-1 spectra, the raw, along with the BIND and the GCM. There was a paper by Byrne and Goldblatt in 2015 about the Archean climate, where they both argued that as high-train inversions have increased, there's been more lines added to the near infrared of the methane spectra, which increases this potential for absorbing stellar energy in the upper atmosphere. And then we use Hydrain 6 2016, which coincidentally adds this spot here right at 10,000 inverse centimeters, which is 1 micron. So even in going from 12 to 16, there's methane absorption added smack right in the middle of where the TRAPPIST spectra is emitting. So this all contributes to why methane itself, independent of haze, drives this significant stratospheric inversion and also cools the surface because that energy can't get through to the surface. Okay, I got to speed up a little bit here. So we took a look at our hazy climates. One of the interesting things that we found here from our hazy simulations was if you look at the right, so I should back up a step and say the way the hazes were injected into the model, we took haze production rates in a mass per unit air volume per unit time, so grams per centimeter cube per second. They serve as a source function into karma, which is fully linked with exocam, and they're injected in the model at a very small size, a 1 nanometer size. And then from there, exocam and karma do their thing. Karma lets them coagulate, diffuse, that there's gravitational settling. Uh, Exocam and advex them around the planet so they can grow in size. And you can see that from the far right, there end up being a few microns in size. We treat them as fractal aggregates in the model. But we actually see that the hazes cause a cooling in the upper atmosphere instead of a warming, as is conventionally thought for simulations like of a hazy Archean Earth. So we kind of dove into this a little bit, and our best guess here are two things. One is the dynamical interaction, that the hazes end up being transported to where the sun doesn't shine. So the poles and the total atmosphere column amounts, and then the night side, the stratosphere, as and the night side for the stratosphere. So the thickest hazes are where the sun isn't actually shining. We also find that the stratospheric haze lobe you can see on the right that gets advected around to the night side on near the eastern beyond the eastern terminator ends up radiating to space a little bit. So that's where we get a little bit of cooling from these hazes. So they're not really absorbing much solar energy, and they end up re-radiating to space a little bit on the night side, where the absorption by methane in the stratosphere is dominating things. And we can see as well the spectral component to this as well. We use the Carre optical constants and then fractal aggregates. You can see the haze mass absorption coefficients here at the bottom compared to the TRAPPIST-1 spectra. And you can see again, it's this radiative coincidence for TRAPPIST that the TRAPPIST-1 spectra, when we use the Carre optical constants, is at its maximum right at this deep minimum in the absorption coefficient for hazes as constructed here. So one of the take-home points is that I think I actually have them on the next slide here. Hold on. Oh. Fractal versus me. I'm going to skip over that for the moment. Uh, One of the caveats here is that the haze problem here is described as quite narrow. Uh, it's this confluence between the TRAPPIST-1 spectra with the optical properties, in particular the Cari optical properties, along with the dynamics of the TRAPPIST-1 rotation rate, baked in, so that if we postulate that if you were to choose like a completely different scenario, in particular, a different stellar spectra along with different optical properties. I know there's groups today that are doing all sorts of different optical properties of hazes with different permutations of gases that vary in different ways. You can end up with different results here and not quite as extreme of a case where the hazes are they're the minimum of the haze absorption is right in the middle of where the maximum of the stellar spectra is radiating. So I think one has to be a little careful in extending these results about the haze to other systems, and instead realize that there's a lot of things here to twiddle with. Stellar spectra, refractive indices, the overall general circulation of the planet, which is affected by many different things. All and also the optical. I skipped over it because I don't have time, but different microphysical assumptions between me particles, fractal particles. There's a whole bunch of different assumptions that go into constructing a fractal particle. All of these things can have an effect on the haze radiative properties in the atmospheres. So this is a big area for future work going into more of these iterations. Uh, so let's see, as we move onward, uh, from this sparse sampled grid, the next step we wanted to do was try to stitch the results from the sparse grid into a coherent picture. And you see on the right from Kriging, which is similar to Gaussian process simulation. Uh, we did that, and this shows the surface temperature. And we did this for a variety of all the different variables, and they're in the paper. I'm not going to go through them all. One of the interesting things that we discuss in the paper, as you can see here, plot CO2 volume mixing ratio on the y-axis, methane on the x-axis. As you increase CO2, the planet warms regardless of the situation. But as you increase methane, it warms up to about a mixing ratio of 10 to the negative 3, about 1,000 ppm. And beyond that, this absorption of stellar energy in the stratosphere, this anti-greenhouse effect, begins to dominate and cool the planet. So we see our coldest climates are at this regime with very high methane, and this actually poses, a which wasn't, we did a very extensive revisions with the in review, mostly because it was a very long paper and there's a lot of questions, nothing damning, so to speak. But one thing they didn't point out was the inconsistency of, well, how do you get, if you assume methane is some sort of biological source, which is sort of the basic premise to begin with, if you get to really high methane, you start to cool the planet and that would kill off life. So, yeah, methane, reaching these high methane concentrations based on a biological source would be self-limiting. However, of course, Titan in our own atmosphere, in our own solar system, proves that you can have a situation with very high methane without life. So we did this Kriging interpolation for all the different variables, ice fraction, water, clouds. I'm not gonna, I don't want to belabor this too much. Some of the, yeah, I'm running short on time. I don't think I need to go through all of these. Uh, One of the interesting things I will point out is that we end up finding lower uh, lower albedos for the colder planets, and this is because the rather than reverse, where you might expect a very cold planet that's covered in ice is bright because it's covered in ice. Here we find the opposite, that the very cold planets that are covered in ice have a low albedo because they're covered in ice because of a strong absorption in the stratosphere by methane that makes the planet look dark, but actually be covered in ice. And it's because all that stellar energy is absorbed in that stratosphere and it doesn't reach the surface, nor is it reflected to space. So our hope in, as I kind of just scroll through these quickly, our hope in doing this sparse grid along with interpolating them all together was to try to see if we can pick out different, relationships across the grid that might not be obvious otherwise, just looking at the individual data points, or might, have required us to do different linear axes of simulation instead of doing the sparse grid across our 2D space here. So some of the take-home points from our analysis, that I've discussed, being methane near IR absorption creates a strong anti-greenhouse cooling, um, and weren't while causing stratospheric inversion. We find that chemistry, and this has been stated elsewhere, chemistry produces hazes for CO2 to methane ratios greater than about 0.2. But there, as I said, the SED optical property relationship is very important. The sparse gridding here allowed us to explore and analyze a wider parameter space than otherwise would have been, easy to do. Let's see. We're hopeful to start applying this now that we've published this paper, to start applying this general method to different planetary systems, hopefully ones that have better observations. So that means we might have to leave the realm of terrestrials behind and start simulating other things. So in the last couple minute or two here, we took our same simulations. We calculated transmission spectra with PSG, and you can see here our four corner points again. High, low, 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 high, high, and low, high for CO2 and methane. And the one that really sticks out, of course, is the hazy case, as you can see with that strong slope across the visible and near infrared and the much higher transit depths than the others. So that sticks out quite prominently. And if we take that case, we look at no haze, artificially no haze. It's a cold planet with very few clouds. The feature signals are quite large. And then we compare fractal versus me, and that there's a different slope. If you were to imagine drawing slope lines that connect the bottom, the continuum bottom points of the spectra, you can see that the difference in aerosol or the difference in aerosol microphysics, which leads to different optical properties despite the same refractive indices. The different slopes may be able to tease out different compositions of the haze. Let's see here. So we also did the same Kriging interpolation plots of the transmission spectra termed in the number of transits to get a 5 sigma detection for CO2 and then also for methane. And this is via integrating the not for a particular line, but integrating the total signal for CO2 and or methane across the spectra using James Webb. And it's, we sort of get these complex shapes. It's not quite obvious. We try to explain it better in the paper, but there's a balance between going on in these plots between the absolute amount of the gases. So more of a gas, the easier it is to see. But the warmer the planet, the more clouds we have, and clouds at a higher level, which make it harder to see. And then we also, at the far right, we start forming hazes, which make things harder to see. So there's not an obvious like one-to-one kind of relationships to say what's the easiest regime to see something in. Perhaps spitballing here, you can see for CO2, high amounts of CO2 in a regime where it's not at the warmest point because that's the cloudiest climate, but it's starting to cool off a bit because it also has high methane, but not high enough to cause hazes to form. So that cools the planet and has this narrow window where it's the easiest to observe CO2. And then likewise for methane, at low methane, it's virtually impossible to detect anything. But as we get to higher methane, and even with hazes present, methane has a more straightforward relationship of more methane, easier to see. And then, so I'm going to end there. I'm at about 31 minutes. I have a bunch of stuff on thermal phase curves after this that did not make it in the paper. We may or may not publish a paper on that. I mean, it's interesting, but it's also relatively unobservable. So the motivation to actually publish the paper is not high. So I will leave it with that and open for questions. And thank you all for listening.
Thanks, Eric. That was great. I'm sorry. Now I feel guilty that we ran it so fast. I don't usually the
No,
slides up
no.
because we want to see some. I probably want to see some
Oh, okay.
slides. So,
Yeah, yeah. Okay. Let me
I mean,
go back
I mean,
here.
just for myself, could you talk a little bit more about the temperature profiles? Because
Hmm.
you didn't have enough time where you had the, extra methane versus not and how that affects, as you were saying that for higher methane, which has been shown in this Goldblatt and Eager-Nash papers, how the
Right.
surface temperatures are cooler than you would expect for higher methane abundances, right?
Right.
And you can see that in your curves here, where they all curve down to the left. Is that right? Do I understand that correctly? At the
Right. So
bottom?
are you seeing the slide here?
Yeah, four
Oh,
basic
okay.
regimes. Yeah.
Okay. So the that little at the very bottom, that little hook back to the left, the
Yeah.
cooler, that's that itself is just an artifact of the typical results, methane or no methane,
Okay.
from the tidally locked planets, is particularly with no ocean heat transport, where
Uh-huh.
you get that the night side being so much cooler, so you end up with these night side inversions.
Right.
Uh, that
Okay.
that's and then when you do an averaging, I mean, as you can see, the dotted and the dashed are antistellar hemisphere and substellar hemisphere. But even
Mhm.
so, you have to get the whole planet warm, right? The whole planet like 300K up before those night side inversions go away completely and stop like influencing these hemispherical average and global mean curves. So that's what that little hook at the bottom is.
Okay.
But just the bottom part here. But you can see, to your point, uh uh the four different cases, right? So low, and then high CO2, low methane. It's quite a bit warmer. High methane cases, you can see that they're colder than, these aren't one to one, like they're randomly, or not randomly, but the CO2 and methane amounts aren't the same. So there's differences, more differences. It's not like a one-to-one comparison for each. But yes, we do see just this very strong anti-greenhouse cooling from
Mhm.
methane that really ramps up above 1000 ppm. And so yeah, I mean, and I tried to explain, it's a stellar thing, is the SCD confluence with methane, confluence with, compared to the Goldblatt and Burn paper, there's even more absorption right at that in the next slide here,
Mm.
right? This, you know,
Right.
point seven is labeled number 7 here in the Hytran release paper, that they added even more absorption, just like coincidentally right where TRAPPIST the spectrum is. So there's some bit of coincidence of effects going on here that one needs to be careful, I stress, in interpreting, carrying these results through to, say, a earlier M dwarf type star, where if it's, consider a 3700K earlier M dwarf star, these all these effects are not going to line up quite as perfectly to maximize the effect as we're seeing here.
Right, right. But I was going to say that this Eager-Nash paper, I don't know if you know about it, but you're on the paper actually, because he
I'm on
sees
the
this in
paper.
there.
Yeah.
He sees it with a completely different SCD. He sees that there's a cooling effect,
Mhm.
right, with these latest high trend
Yes.
things. So it's not just the M
Yeah.
dwarfs spectra. It's It's
Yes.
a more generic effect. I mean,
It is a more generic effect, and I think you're 100% right. And I think what we're seeing here is just the sort of like the maximization of the effect
okay, okay.
because the
This is
way
the
everything
worst case
lines up.
scenario. Right, right,
This
right.
is right,
Okay.
like the worst case scenario, or for methane doing this. But you're right. It's still in the Eager Nash paper. He finds it with or the Earth spectra. In the paper, in our paper that was just published, there was I have a lengthy discussion about comparing this with the same group led by Mock et al. Did simulations of TRAPPIST-1e, and they find cooling from methane, and they look at hazes. So I have a lot heavier discussion there, or comparing the two, where the results from their model and ours are kind of they line up well, despite. I mean, there's some similarities that so they use they also use Atmos, but they don't use fractals. They don't use haze microphysics. They just paste in profiles from Atmos uniformly across the planet rather than doing the full microphysics. But there is, all things considered, there's a pretty decent agreement between the codes.
But I
Hold
guess
on a
Atmos
second.
does only use me scattering, right? It doesn't have any fractal
It
component,
does
does it?
have it does, because I mean I put
Okay.
it in there like a decade ago,
Oh,
and
you
it's
did.
this will
Okay.
give,
Okay. So I
yeah,
was wondering
or
because it
more,
sounded like you
even
said they
more than
weren't
that.
directly comparable, but you're saying that they are. So they, in that
Well,
paper, they
so
do
they
have the
they did
fractal stuff, or they did not
they
do it.
don't. They
Oh,
only
they
use
don't.
me
Okay.
for some reason. So
Okay. Okay.
and in going back and kind of comparing, and then I ran an extra sensitivity test. The difference between fractals and me particles is significant. I will just focus on the top line results, which I put on the bottom here,
It doesn't. Okay, but
where
Eric, looking at this, they don't look that different. Honestly, at these
right.
profiles.
Yeah. I mean, they don't look that different, and the main thing is just the surface temperature effect, that the fractal hazes don't cool quite as much as the me hazes.
Okay.
But
So that's the
I mean,
takeaway. Okay.
yeah. So that's the takeaway. Yeah, yeah,
Oh, okay. I see
yeah.
now. Sorry, I was looking at the plots, not the text at the lower right here. I see.
Yeah,
Okay.
yeah, yeah. The haze mass and the effective radius kind of look the same. Yeah, and it's not, you're right, it's not that different, but that was one of the differences between the papers, is they focus on me. And when we use me physics as well, we both papers find a 15-20K cooling, but if we use fractals, we don't see nearly as much cooling. And so yeah, we go deep into the weeds in the paper. I mean, it was a long paper. There was a lot of people involved, and then we
Yeah.
had a very pesky reviewer who asked a lot of very good questions. But yeah, it made it. It was ironic that the reviewer, one of his complaints is this paper is too long, and then he or she asked a bazillion questions. So we're like, all right, we're going to make it even longer for you.
Yeah.
So
Be careful what you ask for.
yeah, right. Yeah.
Okay. Okay. Well, I don't want to hog all the questions. Anybody else have any questions for Eric?
I have a question. So you're saying that the albedo is lower with the methane because of absorption in the upper atmosphere. So did you try to see? Did you do anything to try to predict surface temperature based on your ensemble stats? And
Did you
I
guys lose my
see that.
screen? I just lost
Okay,
it. Sorry.
No, we see, you see, oh, we see
it's moving.
the presenter view right now.
Uh, okay, hold on. Let me try this again. Sorry, Nancy. I just so
Okay, you get a
give me one
trend.
second here.
Okay, yeah, sure.
Lost this. Where's my screen view? Okay. My apologies. Let me reshare this. Okay. Okay, sorry.
Oh,
Could you repeat the question,
Looks good.
Nancy?
yeah, yeah. So you're seeing this the albedo going down despite
Mhm.
the warming, right? Or no, cooling. It's cooling,
Right.
and the albedo is going down. So did you try to come up with any relationship, but let's see, say what the greenhouse effect is for these planets.
So
Um,
no, we did not. So
okay,
that could be, that would be interesting to do. Or you mean like come up with some sort of parameterized,
yeah, right.
relationship? No, we didn't do that. Yeah, that could be
Okay.
interesting. I mean, I pulled up the temperature and albedo plots here again.
Mhm.
Uh, yeah, I mean, I guess one could do that. One could take the, interpolated, the emulated plot of points from the albedo and derive relationships across each, different CO2 amounts. Yeah, we did not do that, but yeah,
Okay.
it could be interesting.
Yeah. See if where do you get the decorrelation or yeah.
Right.
Yeah. Okay. Cool. Thanks. Very cool, Eric.
Mm,
That's
thank you.
interesting.
So, Eric, did the UM also see these low albedos in their suite of simulations with the methane?
That's a good. That's a good question. Yeah, I think they did. I
Okay.
know. I,
I mean, it's been seen before,
I
right? You're not the first people to see this,
no,
obviously.
yeah, no, we're not the first person to see this because they kind
Because
of
I
go
don't,
hand
for
in
some reason,
hand.
I don't
Yeah.
remember that in the Goldblatt paper that they were stressing these low albedos. I remember the temperature stuff, but I don't remember the albedo stuff, but that might be my
Right,
memory.
right. I don't think they were and I think maybe similar with the Mock et al. Paper and the Egger Nash paper that I don't think they stress the albedos so much, but it's something that kind of, it goes hand in hand that stellar energy is being absorbed in the stratosphere, causing the temperature to increase. So that energy is not being reflected, nor is it going to the surface. So naturally, you have reductions in albedo. So this, I'm not claiming we're the first people to
No.
see this, but maybe we stress it more than others have.
Okay, but can you explain a little bit more? So you're saying the albedo is
Mhm.
quite low. So where does this energy go? You say it doesn't go down, it doesn't go up.
It
What
goes
does
into
it
heating
do?
the strat. It goes into heating the stratosphere.
Right, but then doesn't that re-emit in the long wave? And where
It
does that end
does,
up?
yeah. Well, so yeah, it does. Yeah, I didn't talk about this, but
Because you didn't have
uh
enough time. Sorry.
no, it's fine. I have to find.
Because I think you had a
Give me.
plot for long wave, but
Okay,
you went over
right.
it because
Okay, so
you were short on time,
yeah,
of course.
I
There it
do.
is.
So yeah, this isn't. I don't have the temperature up here as well, but you can see the long wave shows the opposite effect, where you find for these colder planets again on this part of the plot, right, that they have a higher OLR vis-a-vis the
Mm.
surface temperature. So you have this sort of, I think that's one of the things I say in the paper is, so many astronomers, right? They love their 0D approximations of atmospheres where, you have a temperature, you have an albedo, and you have an emitted amount of flux. And, a planet that's darker has a low albedo, it's going to have a high OLR, and it's going
Mm.
to be a hot planet. Where we see actually the opposite, where our very cold planets have a frozen surface and a relatively speaking low albedo and a relatively speaking high OLR. So those two concepts are flipped around
Yeah,
vis-a-vis the hand wavy idea of what one might expect if all you know is the equilibrium temperature and
yeah,
the albedo and OLR.
right. So they better hope they don't get you as a referee next time. Is that what you're saying?
Well, I'm a softie with as a referee. I'm a softie. I asked a couple questions, but I don't want to prevent anybody's career advancement, so I won't kill their paper over it.
Okay, but you will make them cite the appropriate literature,
I
I
will,
hope.
yes,
Yes.
I will make them cite this paper and all my other papers just to fluff my Google Scholar count.
Good, good, good. We need all the help we can get these days.
Yes.
Okay, yeah, now I'm again, I feel bad that I rushed you through this. It was really great though. I mean,
No,
I
yeah,
think
thank you.
you mentioned that you gave a full hour thing at Eddie's, so maybe we can try to find that and if people really want to see the full seminar, they could.
Yeah, he sent it to me somewhere. I can look it up. I'm pretty sure. As I said to you on Slack, I absolutely cannot stand listening to the sound of my own voice, so I have not watched it.
Yes.
But yeah, and then I talk about thermal phase curves, and there were some interesting pieces in that, which I will
You want to
just
show
give
us
the
some of
two.
that? If you want to show us some of that, it'd be kind of cool.
Sure.
I'm curious because with the outgoing long wave, there might be some interesting artifacts there, no?
So we didn't. quite, hold on. We
Whoa.
didn't quite get to the bottom of it. I'm sorry, I'm just kind of skipping ahead. But it's been well demonstrated by many people about how TRAPPIST-1e lies at, actually, I'm going to flip back to this slide here, sort
Hmm.
of this confluence between dynamical regimes.
Right.
Uh, and it's also been seen in the tie simulations,
Right.
where these are the zonal wind patterns that for every different model, every different composition, you get double jets, single jets,
Mm.
different weird structurings of stratospheric super rotation and double or single into surface in the troposphere. So we started to kind of scrape at this again with, our whole variety of phase curves. And, I have some explanation here about the amplitude is important as well as offset. And these two things could be used to kind of determine, uh, uh, maybe start to parse out climate due to heat redistribution. So we did this a similar technique of taking the amplitude here in a normalized context, normalized units, and putting it into this, kriging it across our grid, and the different shapes here, the triangles, the diamonds, and the X's are different uh, hand wavy, if you will, assessments of the dynamical regimes. I forget what they are off the top of my head between like single jet, one big jet, double jet case, or I think one's a triple jet where you have like two in the stratosphere or two in the
Hmm.
troposphere, one in the stratosphere. And you can see sort of this demarcation, they kind of
Mm.
clump together, right? You see the
Yeah, they do.
diamonds that we didn't quite get to the bottom of this. And then we look at the phase offset as well, has even more of a separation between the phase into the, negative being into the Western hemisphere, positive being into the Eastern hemisphere, uh,
Yeah,
between,
there's definitely an offset
so
that separation there. That's really cool. Wow.
yeah, and then this triangle point up here compared to these is actually like, so we originally had this plot in the paper and we decided to pull it out because we felt that in revision, one of the reviewers, not the pesky one, but the other one asked, which I think I know who it was, and they were very, very respectful, and they were like, well, dynamics and all the, and then we got to the point, I made this plot and I was like, this is pretty cool. But I think to actually do a good job at fully explaining what's going on here would have needed more. It needed
Mm.
more quantitative assessments of what differentiates these different dynamical regimes rather than me hand waving and say, well, this kind of looks like a double jet. This kind of looks like a single jet because they're really more of a continuum of shapes, if you will. So there's something here, right?
Yeah.
It's interesting. One of the things that's holding us back from, digging into it is that let's see, I don't think I have a plot, but the signals are small, right? You're talking about thermal broadband amplitude signals. I show them here in normalized units because it looks nice. You're talking 10-20% differences, but you're talking, 0 to 5 ppm, which are not going to be able to be observed with James Webb. So it's interesting, and I've always been a fan of thermal phase curves for how they can, between and I think yeah, between transmission spectra helping you get composition and vertical structuring, right? And thermal phase curves getting the heat redistribution, day night, and clouds, like from Jun Yang's papers showing the substellar clouds and things like that. It could really help you piece together a full picture of atmosphere. But unfortunately for TRAPPIST, we're already kind of scraping the bottom of the barrel here, hoping it has an atmosphere and having transmission spectra, which are, at best, there's no H2. And I don't know, we can't really, at least for TRAPPIST-1e, they're not calling it, calling calling it and saying there's no atmosphere. They're saying maybe there is, it could be, but we don't know yet. So doing the phase curve paper is also it's a decent amount of effort for something that's still angels dancing on the head of a pin. So
Right.
while I think it's scientifically interesting and there's a lot of cool relationships, maybe this would be better motivated for this type of analysis, looking at K218b for, forget about DMS and whatnot, but like a
Yeah, yeah,
planet
yeah,
like
yeah.
that you can actually get a phase, like observable phase curve and start piecing things together rather
Well, there
than
was this archive paper that came out last week on JG251c. Did you see that? Where they're saying it's a really good candidate for direct
I
imaging?
am I am on that paper as well.
Oh,
Yes.
you are. Of course you are. I
Yeah,
should just
yeah.
assume you are. Dude, okay, all right.
I just pop up everywhere, right? Yeah.
Yes, you do. Okay.
Yeah,
So
so
is
that's
it
a
really
core.
better, Eric? Will this plot be more better in that
So
situation or not?
JG251c is a non-transiting planet.
Right.
So I don't know about that planet as far as they're thinking direct imaging, not thermal phase curves. So in that paper, I ran a couple simulations, and then Vincent did PST reflectivity spectra,
Uh-huh.
right?
Okay.
So they're in there somewhere. I think it's mostly just reflected light spectra for
Okay.
that planet as a non-transiting planet, not thinking thermal phase curves. So I don't know. Yeah, I don't know. I'm gonna reserve judgment on that fully. And unfortunately, in that Corey Beard, who's the lead author, he has left for private industry like a year and a half ago, and he just
Oh
really
boy.
wanted to finish up this paper for his own, uh, just for
Satisfaction. Yeah.
pride, yeah,
Yeah.
for his own
Yeah.
satisfaction. So,
So, okay, then let me ask the other obvious question. What about Proxima B? I mean,
I don't
it's
know. Yeah, I
close.
mean that it's
I
closer.
mean,
Yeah, that could be better. Yeah, I would. I mean, Tomas really the one I ask about like these sort of observable questions, and he's a pessimist. I mean, is he most of the time he's like that. We're never going to observe that planet or
it
whatnot.
might be
So
because the inner working angle is too small or something. I don't know, but
yeah, it
yeah,
could be. I mean, and but the thermal emission phase curves, which I like, are different from, I believe, I'm kind of out of my wheelhouse here, from direct imaging, right? Of direct imaging of reflected light off the planet. That I don't think the inner working angle matters for thermal emission because you're getting that difference. You're getting one signal, right? The
right,
thermal
right.
emitted signal from the combined system,
Hmm.
and then you're subtracting out the star
The star, yeah,
and getting that difference and
right,
hoping that you can beat down the noise enough that and be confident that the difference between the two that you're seeing is what you're is like planet only.
yeah,
So
yeah. Like these
so yeah.
secondary eclipse things people have been doing. Yeah,
Yeah,
absolutely.
yeah, the secondary like exactly right. Except it's I mean, and I think that you also need a heavy investment from the time allocation committees, which I
Yes.
don't think we're at that point yet,
Hmm.
because where we keep coming up goose eggs with atmospheres, right? Why do a thermal phase curve on anything until you know from a secondary eclipse you have more confidence that it actually has an atmosphere? So, but
Right.
K218b is one, but
Hmm.
they're no that we know has an atmosphere, but no one they're not going to do it as a 30 something day orbit. But so the first step would be trying to do thermal emission at the quadrature points, right? And then
Hmm.
at all four quadrature points and putting them together to try to get at some sort of a phase curve because at 32 days of observations times however many orbits you need to get is just not going to happen.
No, no, no. All right. People are already complaining JWST is looking at planets too much as it is. So,
Are they okay?
oh
Yeah.
yeah, oh yeah, yeah, yes, yes. The
Yeah. I
non-planetary
stay out
crowds.
of it. I stay out of
Yes.
it. Yeah.
Okay. Any other last questions for Eric before we call it a day? Okay,
Actually,
then I'm gonna.
can I see the plot of the observation simulation again? Let's see.
Uh let's
The
see. Like the transmission spectra?
Yeah,
Okay. So the actual transmission spectra or like the
there.
interpolated plots?
Oh no, that's fine. Okay.
Okay.
Okay, thanks. That's all. I just want to check out. Look at your paper. Thanks, Eric. That was great.
Yeah, of course. Yeah, of course.
Mhm.
And I guess I'll finish as long as I got 2 minutes here. My favorite slide that I made in Eddie's that I'm seeing here at the bottom. So Exocam is still, as long as I'm funded, it's still going, but right now it kind of is in the garage. It looks like this. It's all in pieces. I've got
Oh
all these
God.
different, little things that Russell Dietrich put in oxygen, O2, and all this continuum. I have an 80% working CO2 ice cloud model. I got the Karma hazes. I've got a student or it's not my student, but a student in England has updated the convection and the dynamics and has been running it for mini Neptunes up to like 1,000 Kelvin. And I need to
Wow.
improve the K coefficients for that. And I'm doing this volcano project with Tomas. So it's like a mess right now. There's a lot going on. So the publicly available version doesn't have like a lot of the recent advancements. So if I stay funded and I don't find myself working at Burger King next year, I hope to put it all together and get ExoCam 2.0. So that's the plan.
Good luck, Eric. That's
All
great.
right. Yeah. Thank you. Right. Thank you. Would you like fries with that, Mike?
Yes.
I'm practicing for my new career.
Need the carbs, man.
Yeah. All right. Thanks. Thank you all for listening and indulging me in my talk here.
Yeah,
Thank you
thank you
for
so much,
indulging
Eric.
us.
Yeah.
Yes, 100%. Okay, we'll meet up again in a couple weeks then. And thank you again, Eric. That was really fantastic.
All right. Thanks, guys.
Okay, see you all soon.
Mike,
Bye.
can you stay for